So as I bring up this next talk, when I first came here back in 1987, it seemed like whether you were doing clouds and aerosols, dust, sort of things that I was doing, or whether you were doing tree balls, which many other people were doing here, we really didn't care about the surface. Right? We just set it flat, and we were done. But then as things went on and we began to birth the Modis cloud mass with Paul and Kathy and Chris Muller and Rich Fry using the MOS data, all of a sudden all these little square things began to show up in our retrievals. And it turned out it was the surface. And so now we're all struggling with how to deal with the surface. Both visible, infrared, UV, microwave, whatever. So I thought it would be good to get somebody up here, Zhenlong in particular, to talk about what do we know about the direct properties of the surface.
Okay. Thanks, Steve. I think you talked a lot about the importance of the emissivity, so which I'm going to talk first here. Then outlines. Then I will talk about how to measure the emissivity. I will present you our evaluation of some of the emissivity product, and followed by the diurnal and angular variation of the emissivity, and at the end, the summary. So this is a slide I'm sure a lot of you have seen already many times. These bars here are just the focus error reduction by different instruments. So the good news here is the IRZ and the AIRS are the two single instruments that contribute to the focus error the most. They're the most. And actually, there's a better news. A very small percentage of IRZ and AIRS radians are assimilated. So why this is a better news? Because just imagine how the weather forecast will be like if we are able to assimilate the window channel radians. And one big problem there is the emissivity. The emissivity is also important for the climate study. And if you look at the bottom two panels here, in this study they found that by using an emissivity of 0.9 instead of 0.96, that's the default value, they found that the simulated surface air temperature could have a difference larger than 0.5 in a lot of areas, and in some of the areas that's larger than 1K. These are quite a large difference for climate study. And I'm sure a lot of you know emissivity is very important for many scientists satellite products. The bottom line here is if you need to do radiative transfer calculation, you will need an emissivity. So the emissivity can be measured in the lab quite accurately. Here are the example of the emissivity of the all the materials you can find on the Earth's surface. So we can see here that emissivity has a lot of spectral variations, and you can also imagine they should have a lot of spatial variations because just depending on the surface types. And if you need a decent spatial variation, you will have to rely on the satellite. Here I have 6 different satellite-derived emissivity product for 8.7 micron. From the bottom to top, the operational mode is from Terra, Alpha, and the operational airs from ascending orbits, descending orbits. And this is the UWIR image by Eva, she's somewhere. And the IRZ from NASA NANI. So just look at these figures. I would like to say they look somehow different. And for 10.8, I don't know, maybe they look quite different. For 12, except the bottom two, the Modis, they are very different. So if you are a user, you look at this, you will have question which one of them has the best quality and which one we should use. So we developed an objective method that uses satellite radiance to quantify the emissivity precisions. This technique uses a double difference technique, which which is first published by Dave Torton. And the double difference here is the calculated channel difference minus the observed difference. The advantage of this is that this double difference is very, very weakly sensitive to the atmospheric profile errors and then the surface temperature errors. So you can directly relate the emissivity precision to the double difference. So here are our results. These are the precisions. The UWIR image is clearly a winner. For 8.7 micron, the precision is just smaller than 0.06. 10.8 smaller than 0.01. 12 is 0.016. And it's very close to the operational modest product, but with slightly improvement. The high spectrum product here is kind of disappointed. For 8.7 micron, it's all larger than 0.03. For 10.8, larger than 0.02. For 12 micron, the IRs is okay, AIRs is larger than 0.03. So I'm sure you know which one you should choose. Okay, for the GOZAR project, we originally worked for the GOZAR. That's when I started working on the emissivity. So for the GOZAR project, we developed a retrieval algorithm based on the concept of time continuity, which was first raised by Paul. So we developed this algorithm applied to severity, and here are some results. The top panel is a UWIR image. These are for 8.7 micron. The bottom two are retrieval. The daytime and nighttime. Daytime is, I think it's 14 UTC, and nighttime is 2 UTC. They look very similar to each other. These are actually very nice. If you compare these results to the Google map, the satellite view, you will find that these spatial features here correspond very well to the visible image in the Google map. So, but if you look carefully, the daytime and the nighttime, there are actually some differences, and this is better illustrated here. These are the day-night difference for the 3 channels. The difference is quite substantial. This is actually very significant for, I think, for 8.7 micron. In some of the area, the difference is actually larger than 0.03. So this indicates there might be some temporal variation. So actually there's diurnal variation of the emissivity. For the different, for 3 channels, and a different color represents different time period, and we can see the diurnal variation there, especially for 8.7 micron. The general pattern is during nighttime, the emissivity is usually larger, and as you go to the daytime, the emissivity will decrease. Then after maybe 13 UTC, it will increase. So when I first saw these results, I was very nervous because we have never heard about the emissivity diurnal variation. It might be reasonable to see some seasonal variation because the vegetation cover change or snowfall, things like that. But the diurnal variation, that's very we didn't see that before. So I did some literature review, and we think it's related to the soil moisture. The reason for that is because in these controlled experiments, these guys did these experiments, they found that the emissivity will increase when you add water to the soil samples. And this guy, he found that the modest emissivity has a positive relationship to the soil moisture by the EMSA-E in some of the area in Sahara Desert. So if the emissivity diurnal variation I showed in previous slides is related to the soil moisture, there should be soil moisture diurnal variation. That actually has been reported by these studies. As an example, this is the soil moisture diurnal variation at different depth. For the very top 1 centimeter soil, there are very strong diurnal variation. And the pattern here is it will decrease during the day. It will decrease until like 3 o'clock in the afternoon. After that, it will increase until about 5 o'clock in the morning. Then after the sun comes out, it will decrease again. So this actually matches quite well with our emissivity diurnal variation I showed in previous slides. So this makes us think if the emissivity diurnal variation is true, we should be able to see that signal in the brightness temperature. So again, we rely on the double difference technique. I cannot go through details here, but the bottom line is if there's the emissivity diurnal variation, we should see a similar diurnal variation in the double difference. That's exactly what we see here. The left is the daylight difference of the emissivity. The right is the daylight difference of the double difference. I think the left and the right match quite well here. So these results actually indicate that our retrieved diurnal variation of the emissivity actually comes from the severity radiance observation, and it's not an artifact of the retrieval algorithm. But there is still a possibility that the severity radiance observation might have some false diurnal variation, maybe due to calibration or something. So what if we look at a different radiance observation? So we use modus alpha here. I don't have to explain these figures, but what we found is that both severity and the modus alpha, they found that they see the emissivity diurnal variation with a very similar magnitude. We also found the emissivity angular variation a very interesting topic. These slides here show the broadband emissivity between 8 to 14 micron of water on the top and ice on the bottom. So the general emissivity will decrease as the zenith angle increases. And this is most significant when the angle is really large. I think these are very important information for instruments like MODIS, VIAs. They could have very large low zenith angle. The MODIS, I think the max low zenith angle is like 65 degrees. Anyway, for the land, it's a little more complicated because you got so many different types of soil and vegetation covers. But in this recently published paper, they studied 12 different soil samples, and they found a similar feature that emissivity will decrease as angle increases. And this impact is more significant for the sandy soil. So as an example here, this is a soil sample with 99% of sand. Different colors represent different spectrum. I don't know, maybe you cannot see the but in general, the emissivity will decrease as the angle increases, and the difference between nadir and 70 degree could be larger than 0.1. Okay, summary. So we quantified the emissivity precisions of some of the emissivity database, and we're happy to see that EVA's product has the best quality here. And we found that in our retrieved severity emissivity, we found the diurnal variations, and we demonstrated that those diurnal variations can see by both the severity and the bodies. And the angular dependence, the general pattern is that emissivity will decrease as the angle increases, and this is quite significant for water, ice, and the sandy soil. So the last bullet, I just leave that to you guys to read.
All right, so Alan.
I enjoyed your presentation very much. Just two quick questions. One for
we can somehow know the soil moisture information, we can have a model or something to add some temporal information to correct the emissivity and also the angle. I think that's something we also can do. So.
Yeah.
So I would like to add that for classification purposes that our emissivity data is already between the optical forward model and it's an optical plan, and the optical will allow you to do some angular corrections.
Well, is Jim still here?
Yes, I am. You want to comment on this, Jim?
Why don't you answer Alan's question? What accuracy do we need in surface emissivity before you can nibble?
Okay, well, the first question had to do with using surface channels. And NCEP does use surface channels over ocean because we think we have a good surface model. Okay, it's over land, over ice, where we start running into problems. And there, usually the surface channels are rejected. Okay, I want to comment a little bit on the angle correction. In the past, I've seen that can be contributed to the radiant transfer model. When I use SARTA versus CRTM, I've seen differences in how the scan angle dependence especially at the high scan angles. So I would suggest being careful about the radiant transfer model you have here.
Okay, I have a comment about this. We actually recently compared the Untitled, CITM, and SARTA, and we did pay attention to the angle. Looks like in the newest version of the SARTA, of the CITM and Untitled, we didn't find the obvious angle difference between them. So.
Because McNally has done a lot of this work over ocean, and he has found problems with scan angles with various radiant transfer models. I would suggest talking to him on that.
Okay.
And to answer Paul's question, the last one, it's been my experience that we're going to need a surface emissivity model that is close to the Haney delta T of the instrument. So if you assume a 300 Kelvin surface temperature and you assume something like a 0.3 Haney delta T, you can do the math and see that you need a very accurate emissivity.
0.3K, I think it's like that's a smaller than 0.01
Oh yes.
for emissivity.
Some of the work I did suggest has got to be in around 1.005, plus or minus 0.005.
Okay,
I can't let that comment be the last one on that point. I think I put that back on the 1D bar data simulation to incorporate the climatology from these sort of a priori satellite measurements, but then to retrieve that emissivity within the field of view of the radiances, and then retrieve it to the accuracy that you need, consistent with the other variables. I think that's the only way you can really take advantage of windbridge over land. With the climatology from the a priori measurements, that's what gives you the chance to do that.
Right.
And I can help you with that.
Good collaboration. But it's fascinating, in terms of anticipating discussions. We went from, as I said at the beginning, where everybody was neglecting surface to a talk now where most of the discussion was about what the heck we're going to do. It's pretty fascinating.